Welcome year 11 Maths students. This is the last topic in chapter 2, which we're going to investigating the geometry and along with the equation of simultaneous linear equations. Previously in chapter 2F, families of straight lines, we've talking about having restrictions on either the gradient or the y-intercept. So we're going to use this concept to explain the three cases in simultaneous linear equations. There are three graphs that I have listed here. As you can see, that the first one shows a unique solution. When we're trying to explain what is happening here, so I'm going to write the two equations. Y equals to, let's say this is m1 x plus c1. And here you have y equals to m2x plus say 2. Okay, in order to have a unique solution that based on the previous knowledge that we know, as long as the two straight lines are not having a equal gradient, right? As long as the two straight lines are not having an equal gradient, they will eventually intercept. And when they intercept, the interception point, it is going to be the solution that is satisfied for both equations. Okay? In this case, if we're saying you have the two straight lines, which you can express as y equals to mx plus c, we only need to restrict the gradient to make sure that the two gradients are not equal. As long as the two gradients are not equal, we will be expecting to see a unique intersection. Okay. Now, the second case is you can see that there are two straight lines technically, the red and the blue, and they are coincide. So when you say the two straight lines are coincide, that tells you the two equations are exactly the same, right? Are exactly the same. I'm going to also write out m1 x plus c1 y equals to m2x plus c2. So in this case, so the m1 should equals to m2. At the same time, c1 should also equals to c2, so that the two equations are exactly the same. There are infinite many solutions, as each point on the straight lines will be satisfied for both rule, which technically is the same rule. Yeah. The last case where the two straight lines or the two linear equation has no solution, that means the two lines will never meet, which means we have to make sure the two straight lines will be parallel. In order to make the two straight lines parallels, we have to restrict the gradient being equal, yet the y-intercept cannot be equal. Okay, so those are the patterns that we can find for each of the three cases in solving simultaneous linear equations. Okay, now let's look at this example here. It says the simultaneous equations x plus y equals 6 and 2x plus 2y equals to 12 have infinite many solutions. Describe these solutions through the use of a parameter. Okay, so firstly, we can highlight here, they're saying they have infinite many solutions. That basically tells us the two equations are identical. They are the same, okay? It's good to show that, we have undergo this process and they are exactly the same, which they should be, yeah? I'm going to transpose this equation to make y the subject. So I can write as y equals to negative x plus 6. As for this one, 2x plus 2y equals to 12. Again, transpose the 2x becomes negative 2x plus 12. And then divide by 2 for either side, you got negative x plus 6. So they are exactly the same, yeah? Now, What does that mean by describe the solutions using the use of a parameter? Okay, the parameter is we're going to using a pronumeral representing either the x or the y, okay, either your explanatory variable or the response variable, so that we can use an expression to represent both x and y values, okay, so that it can representing all the solutions. We can do both ways. We can either let x equals to a number. We can let x equal to, let's say, a. Therefore, you can sub x equals a into, let's say, this one, either one, because they're the same, yeah? So that y is going to be equal to negative a plus 6, yeah? Or you can write it as 6 minus a. So now we can say when x equals a, y would equals to negative a plus 6. This will be including all the possible solutions. Okay, when a equals 1, you get the y equals to 5. When a equals to 2, you get 5. You get the y equals to negative 2 plus 6, which is 4. Okay, and so on. We can also let y equals to a parameter. Okay, we can set the y being a parameter here. Let's set y be b. Okay, so then you have b equals to negative x plus 6, and then we got x that is equal to 6 minus b. Okay, you can say when x equals to 6 minus b, y will equals to b. Both should be considered correct, as they all representing the same relationship here. So lastly, for this one, don't forget to describe what is A and what is B. Like, what are the type of numbers that we can choose? So we can say here, A is a real number. Yeah, A is a real number. Here you can say B is a real number. Okay. Okay, now let's look at the second example. They ask us to find the values of m and k. So when they say they intersect at the specific point, when we can actually substitute that particular point into the equation so that we can find the missing unknowns, right? Now, when we substitute 2, 8 in, so you need to be careful that you substitute the right one first. Because the first equation, this one, only has the one unknown m, okay? While for this one here, you got two unknowns. You got the m and k both unknown. So you can't substitute into the second one, and otherwise you will be ended up with two unknowns you can't solve. So when you substitute into the first one, like what I did here on the left, so you can actually find m, which is just a linear equation. You find out m actually is equal to 0. And then you can substitute m equals 0 along with the x equals 2 and y equals a into the second, and then you can find out that k is equal to 24. So these are the two examples that we're using the ideas that we have summarized for the three cases in simultaneous linear equations. I hope you like these videos, guys. Also, if you have a time, try to complete the chapter 2 review questions. Start from next week, we will be working on chapter 3, quadratics. Thank you for watching. See you next week.